Electrical power is required in order to drive the motor that connected to the impeller in the vessel. The power is required to overcome the viscous forces of the broth in order to have a uniform mixing, and it's a function of viscosity, density, presence of suspended solids, speed of agitator, type and nature of the impeller. The power requirement that being calculated does not include the power consumed by the gearbox assembly, stuffing box, O-ring or mechanical seals, friction in the motor and assembly, and other mechanical losses. The actual power requirement of motor is more than the one calculated. When a fermentation system is parched with gas, the broth around the impeller is less dense and requires less power. For the requirement of ungassed Newtonian fluids, the power consumption for stirring non-aerated fluids, meaning we did not sparge any gas in the fermenter, so it depends upon the fluid properties based on the density and the viscosity, the stirring rotation rate, Ni, the tip speed or the rotational speed, the stirrer diameter, Di, the drag coefficient of the impeller, CDI. The relationship between these variables is usually expressed in terms of the dimensionless number, which is the power number. This is a typical power curve for various types of Rushton impeller, paddle mixer, and a marine propeller. So based on the Reynolds number that we have calculated, we know which region that it belongs to, whether it is a laminar, transition or turbulent. That from this curve, we may able to identify the power number for the impeller itself. And this is a typical dimensions for the impellers with buffer. So you can use this figure ratio, dimension ratio, in order to design the impeller. In the turbulent region, the power input is independent of viscosity, mu. Whereas in laminar flow, the relation is more nearly given by P alpha Ni squared Di cube. So this figure, you can see here ABC is referring to the type of impeller, and S1, S2, S3, S4, S5 till 6 is the ratio based on the dimension of the rector. It is being given here. So based on the ratio, example dA over dt, dA the diameter of the impeller, over diameter of the tank is equals to 0.33. So you can use this ratio also in your calculation for design. In the laminar region, power number is inversely proportional to the impeller Reynolds number. The power required for laminar flow is independent of the density of the fluid, but directly proportional to the fluid viscosity. And the power required stirring of ungassed liquid is given by the equation here, alright, where Ki, can see Ki, is the proportional constant. In the turbulence region, the power number is constant irrespective to the Reynolds number. So the NP is the power number. NP here is the power number in the turbulent zone. As for transition region, both the viscosity and density of the fluid have effects on the power requirement. So NP is obtained from the graph. The table here shows the constants, okay, for the Ki, alright, and also the power number for each of the impeller type.